Okay then. So let's go. Can you hear me? Can you hear me okay?
Yes, perfectly.
Okay. So guys, welcome. Good afternoon to everybody. So I hope you guys I don't know if you've seen the slides for the yesterday's lecture was made available today. I'm sorry for that. I had to correct some things and I got mixed up in some other stuff. So, but they are available today. I guess this morning they were available already. I don't know. I think they were. So if you guys want to check it out or anything that might have not fully, I don't know. So they're available now. Okay. Okay, so let's dive into today's subjects. I think I finally found a way to get rid of that annoying floating bar. But okay, so let's go. Lecture 3 in this mini course series. Um, I want to spend a couple of minutes talking about yesterday's lecture just to make sure that we all appreciate what we did yesterday. Okay. Sometimes the content is too heavy, so we are, I don't know, not in a place intellectually to really appreciate what we've done. So I want you to take a moment and retrace our steps from yesterday, okay? So we started from a metric perturbation, okay? From a metric correction, all right? What this means is that we are decomposing our geometry, right? We are the metric, after all, fundamentally gives us information about the geometry of our space-time, okay? So what we are doing is we are considering a decomposition in which our spacetime can be modeled as a flat spacetime plus a small perturbation, right? A small correction. And what we did was we plugged in this correction into the objects that we know that we must construct to compose the Einstein field equations, right? And keeping to first order in this correction, in this perturbation, we constructed a linearized version of the Einstein tensor, and thus we were able to construct a linearized Einstein equation, okay? So we went from a highly nonlinear set of equations to a set of linear equations by this decomposition here, okay? And then we saw that if we chose a gauge properly, with the right choice of gauge, we were able to simplify our equations even more and get to this equation here. And that it's just phenomenal, right? When we already know where we are gonna end up, we don't fully appreciate what is happening here because you see, this is a geometry correction, right, to our metric, right? This is a wave that behaves as a wave. After all, this is the homogeneous wave equation, right? So we have a wave of geometry of sorts that it's a physical thing, right? That propagates through space-time. We discovered that it travels in the speed of light. We discovered that it has only transverse polarizations, just as the electromagnetic waves. We saw that it can be modeled, it can be thought of as a massless spin 2 field propagating in flat background. And this is kind of amazing, right? Because you see, this subject was not at first studied to obtain gravitational waves, right? this historically, if I'm not mistaken, this starts with the question of how stable our space-time is, right? So we have our space-times, Minkowski space-time, Schwarzschild space-time, and so on. And the question is, how stable are they? So we do a small perturbation to see if our if our space-time is stable, right? And what we discover is that when we do that, this perturbation will propagate as a wave, right? So, I mean, I think this is kind of amazing here. I opened up this operator for you guys to see more clearly that this in fact is the wave equation, right? So, and what I wanted to do also was to give you a little demonstration here, let's do some visuals here for you guys to see. I don't know if the video is already playing for you guys. I think it is. So here, well, he's doing exactly what we did yesterday, right? This is basically the wave equation, right? Here he states that the K is the wave number, H0 is the amplitude, which we call the P plus and P cross, right? For the polarizations. So in this example, he did he chose the direction of propagation in the z-axis. Okay, that's why his polarization matrix here is a little different. Okay, it's completely analogous to what we did. Here he's doing different points in time, right? To see what happens. So he does the cross and plus polarizations. Okay. So now we're gonna see exactly what we saw with the group of particles, the set of particles in a circle, or arranged in a circle, and see what happens, right? So the distance between these 2 points when the perturbation is 0 is given to be 1 meter, but when with the perturbation, this distance would be increased, right? If the perturbation here is, if the delta that we saw previous lecture is positive, and the same thing will happen in the y-axis, right? If the perturbation is positive, right, the distances will decrease. If it's 0, will remain the same, right? And if it's negative, the distances in the y-axis will increase, right? Because it's a minus sign here in the y direction. So here he does the same with what we did for the arrangement of particles in a circle, but he does with a square, okay? So let me get back a little. So this is the propagation as what happens to the square as the plus polarized wave passes. And now what happens to the square when a wave cross polarized passes? Okay. And thus, as a wave passes, so somebody asked me yesterday about the scattering of electromagnetic waves, of gravitational waves, sorry, in massive objects. And the thing is, it passes through because the coupling of these gravitational waves with matter are very weak, right? But yes, the gravitational waves do scatter from potentials, and that is the basis of the quasi-normal mode study and so on and so forth. So now that we gained a little bit of perspective, let's do perturbation theory in curved spacetimes. Okay. So, well, we're gonna talk here about some general backgrounds. Okay, I guess I'm gonna have to keep shifting this from time to time. Um, Okay, so we're gonna do general backgrounds. What this means is that our background metric is no longer a flat metric. Okay, it is a curved metric, but we are not saying which metric this background is exactly. So it's a general curved metric, curved background metric. Okay. So we will see what happens as we do small perturbations of a background metric G with this little circle, with this ring as on top here, which states which represents the background metric. And this small perturbation will be generated by some source, which is this delta T mu nu. Okay, T mu nu ring here, T mu nu dot, if you prefer. T mu nu circle, I don't know. This is the source of curvature for the background metric, and this delta T will be the source of the small perturbation. Okay. Um, so the full metric is G mu nu. It's, well, here from previous lectures, we had eta mu nu because it was the flat Minkowski metric, but now we have a general curved metric. And then some perturbation, delta G mu nu, okay? Which we used to call age mu nu, and we will again, but only to generalize things a little more. We're going to use this notation, but it is the same thing. It is exactly the same thing as age mu nu, okay? And here we have that that condition for the perturbation to be very small, right? Which we now know that we can preserve as long as we find the right infinitesimal transformation, infinitesimal diffeomorphism, and calibrate this vector here appropriately, so to maintain this condition and to maintain this condition that the perturbation is very small compared to the background components. Okay. All right. So this is the G inverse, right? Which is exactly as we saw earlier in the flat background, right? This minus sign is here to make sure that when we contract G mu nu inverse with G mu nu, that we're gonna have the identity matrix. Okay. Exactly what it is doing here. Okay. Plus some terms that are negligible, right? From the from higher order terms in H. Okay. Which should be in higher order in delta G right here. So I'm sorry for that, for that mistake, but I can correct it later. But yeah, okay. So these are the Einstein equations, right? G mu nu equals to 8 pi T mu nu, where G mu nu can be defined as such, which it depends on the Ricci tensor, the Ricci scalar, the metric, and so this is the Einstein equations, okay, where you can always decompose these tensors such that the Ricci tensor will be the background metric, Ricci tensor plus a small perturbation. To understand who these guys are, we're gonna have to do the same thing we did yesterday's lecture, which is to plug in the full metric in the objects of the Christoffel symbols, and then the Riemann tensor, then the Ricci tensor, and then we're gonna separate the objects with this ring from the objects without it. Okay, and the objects that we're going to identify as the Ricci tensor from the background, and what is left is going to be defined as the perturbed tensors. Okay, we didn't have to do this previously because our metric was flat, so this would be zero for the Minkowski metric, right? Trivially zero. So this is why we didn't do things this way previously, because we didn't need to, right? The Ricci tensor will be 0 for flat metrics, the Riemann tensor components, and so on. And so, but now that we are dealing with a curved background, a general curved background, we need to do this decomposition in more detail, right? And the same goes for the T mu nu, and the same goes for the T, which is basically the trace of this, okay? Which is taken, the trace which is taken with respect to the full metric, keep in mind, okay? So let's go. Well, remember that, well, we have this as the definition of the Ricci tensor, right? And this is the definition of the Christoffel symbols with respect to the metric components, okay? The equations, the calculations are gonna become very convoluted now, very nasty, okay? But don't be afraid, okay? I'm here with you guys, and we're gonna push through this. And the thing is, things in physics sometimes get nasty, and we have no choice. Okay, but bear with me. We're gonna get through this. Okay, together. So okay, the next thing we need to do is to find who are these guys, right? Who is the delta, the perturbed Christoffel symbols, and then with this find out who are the perturbed Ricci tensor. Okay. So first we define this version of the connection of the Christoffel symbols, right? With the upper index lowered, which we achieve by applying the metric, right? If we apply the metric to the original Christoffel symbol, right, and contract the indices here, so we get this expression, right? This contraction of G with its inverse will lead us to a Kronecker delta, okay? And what the Kronecker delta does when it contracts with some index, it's that it relabels it, right? It changes the index name, right? It changes from, in this case, from beta to sigma, right? In such a way that we get this this expression here. Okay, so this is the form of this completely covariant. I don't want to say covariant, because this does not transform as a tensor in principle, but yeah, with all the lower indices. Okay. So now what we're gonna do is we're gonna use this operator. We're gonna do this delta as a derivative operator, right? And we're gonna apply it to the Christoffel symbol, which we can now define as a contraction of the inverse metric with this new Christoffel symbol that we just constructed. Okay. And using the product rule here, we get to this, right? We do the variation with respect to G, and then the variation of the variation of G, and then the variation of the Christoffel symbol, right? Just as we would do with the derivative operator, okay? But the fact is, who are these guys, right? Who are these elements? Who are this element and this element, right? Well, I'm not going to do a full proof of how to compute this object here, but you can see the full development in the book by Ferrari and Paulo Pani, on one of the references, okay? So one may prove that this object here can be written as this other object here, okay, which is the perturbed metric, perturbed full metric here, okay, and G here, okay. So in a way that substituting this into the expression, okay, substituting this into here, we get this, okay. And we see that this metric here is contracted with this index here, which raises it, right? And we get back the original Christoffel symbol. And then we have this expression, okay? Changing the dummy indices, well, alpha to sigma, which we can do because they are dummy indices, right? So here, what we're going to do is going to change this dummy index here, this dummy indices here, which alpha, and turn this into a sigma, okay? In a way that we get this, okay? So now we changed alpha to sigma, right? Which we can do since they are dummy indices, right? In such a way that now we can take this element that is in both terms here and put it in here, okay, in evidence here. Okay, so now using the definition of our new Christoffel symbol with lower indices, we arrive to this expression here, right? Just a second so that you can appreciate what we are doing so far, right? We're gonna do this. We're gonna open up this term here, okay? This is what we are gonna do. And when we do this by using this as we did earlier with the product rule, but then we as another derivative operator, it commutes with the partial derivative, so we can just apply this. So the variation of all this gets to this, right? Substituting this into this expression here, we get this, okay? So we get this full expression here, okay? Note, however, that these two terms here are a little bit familiar, right? We get a partial derivative of this object, and then we get this object contracted with a Christoffel symbol, right? I don't know if it's ringing any bells, but this kind of looks almost like a covariant derivative of this term delta G nu sigma, right? Almost like, because the covariant derivative of a 0-2 tensor would need another term, another Christoffel symbol term here, contracted with the other index of the tensor, right? And the same goes for this object here, right? So this is the covariant derivative just up to a term in the Christoffel symbols, right? So if we do this identification, right, this is our almost covariant derivatives, but they are not yet. So what we do is this, right? So this is the covariant derivative plus this term gets us this, okay? Which is the same as to sum and subtract the missing terms, right? It's the same thing. So we saw that, well, the red term can be thought as a covariant derivative of this object plus this term contracted with the Christoffel symbol, right? And the same goes for the blue one, right? For the blue term, okay? But now, if we take this term and this term, right, and associate these two terms to this derivative here, we get this, right? So we have this term here, this term here, this term comes here, and this term comes here. And if you see, this is exactly the covariant derivative of delta G mu nu, okay? Which is exactly what we see here in the last line, okay? So this worked out pretty neatly, right? This practically very conveniently worked out for us. So finally, we see that if we open up the full inverse metric, right? Remember that this inverse metric is equal to the background inverse metric minus the inverse of the perturbation. So if we do this and keep this in first order in the perturbation, right? We get this expression here, right? Because there would be a minus delta G here, so but the delta G inverse multiplying these terms here would give us terms in second order in the perturbation, right? Which are contained here, okay? Again, I'm very sorry about the age here. It's completely analogous. So G is delta G is H. So but we haven't identified this yet, but okay. Anyways, so this is the expression that we get when we open up the inverse metric, right? Now we have here the background metric, which it's exactly what we obtained for the Christoffel symbols in the perturbed Christoffel symbols in the flat Minkowski metric, right? Here would be eta, right? Here would be eta, and here would be the perturbed terms, right? And okay, so let's see. The thing is, this object here is a tensor. And the thing is, the Christoffel symbols, the original Christoffel symbols, are not tensors, right? We saw that they don't transform as tensors, right? But remember that the covariant derivatives, right? They map objects into tensors, right? If they act on a scalar, right? They map scalars to 0, 1 tensors. If they act on contravariant vectors, 1, 0 tensors, they map the 1, 0 tensors to 1, 1 tensors, right? So you see that this object is clearly a tensor, even if this wasn't a tensor, which it is, right? This is a tensor. But if it wasn't, if this was a scalar, right? This object here is a tensor, and this is a tensor, and this object here is also a tensor. And the sum and subtraction of tensors form a tensor, right? So this is what makes this object here the variation of the Christoffel symbols are in fact a tensor. And this is very much analogous to the fact that the difference, right, between two different connection coefficients form a tensor, right? I don't know if you guys remember from the first class, from the first lecture, we saw that as we construct the Riemann tensor, right? When we take those different directions that we in that closed loop, when we transplant the vectors and so on, we get what is called a torsion tensor, right? Which we identified as 0 because we're working in a space-time without torsion. So this leads to the Christoffel symbols being symmetric in these two lower indices, right? But the fact is that the difference between two different types of connections form a tensor. And the variation is very analogous to this, right? This can be can be seen as the difference between our original, right? Or our original Christoffel symbol plus some other term, right? Some other Christoffel symbol, okay? You can check this on Wald. He does this development very clearly about different kinds of connections. If when he's wondering if there is a different connection in our space-time, right? But we saw that the Christoffel symbols are the only connections that make so that the covariant derivative of the metric is equal to 0, and so on and so on. But yeah, okay. So we get to the fact that the variation of the Christoffel symbols form a tensor, okay? So the perturbed Christoffel symbol is a tensor, okay? Applying the same reasoning for the Ricci tensor, right? Okay, I warned you guys that the equations were going to become a little convoluted, but there's nothing to be afraid of here, nothing to worry, because we are just applying this derivative operator, like this variation here is a derivative operator. So we took the derivative here, we commuted with this and commuted with this partial derivative and applied the product rule here, right? We apply the product rule. So in fact, what we get is this full expression here, okay? Here we have this variation of these two terms, which open up in other two terms here, right? Because of the product rule. The same goes for this one, which opens up also as a product rule. And we see we need now what we're gonna do is to substitute the expression that we got for this guys here for the perturbed Christoffel symbols, right? In each slot here and see what this gives us, okay? So we're gonna rearrange and identify some terms here. So in such a way that we get to this expression and this expression here, right? Which is basically, right? The same as a almost, right? You see that the second term here and this term here, they cancel, right? This term here is exactly this term here with a minus sign. So these terms cancel, and we are left off is the rigid perturbed Ricci tensor, right? Is that okay, guys? I don't know if it's clear. It's important that every step of these calculations, it's clear because to see these calculations, these computations, anyone can pick up the books and look at it, all right? What I want to do different in this, what I'm trying to do different in this mini course here is to really get into the full details or maybe almost all the details in the computations regarding the perturbations, okay? So if there is any questions, any sort of trouble in some passage, you interrupt me. Victor, if you see something in the chat, also you can always interrupt me as we did in the first lecture. So yeah, so is there any questions so far as what we did so far, right, with the Ricci tensor and the Ricci and the perturbed Christoffel symbols?
At least in the chat, no questions so far, Vitor.
Okay, so I'm going to proceed, right, because we have a lot of ground to cover today. But let's go. So this is what we call the Palantini identity, okay? So this is, you see that this is not really necessarily related to perturbation, right? We are identifying this variation as due to the perturbation, right? But as you work with the Lagrangian formulation of general relativity, you're gonna find yourself in the middle of computations like this when you want to understand better what it means to take the variation of the Ricci tensor or the Christoffel symbols and so on. So, what we are doing here is identifying this variation as the perturbation, right, of the metric, right? So what is causing these variations are the perturbations, okay? So they are interchangeable, right? So we think of this delta as representing the perturbed tensors and the perturbed quantities and objects. But yeah, this Palantini identity is not necessarily related to perturbation theory, right, in general relativity. But okay, so let's go. So using these expressions here, right, because now what we're going to do is going to substitute these terms here. We simplified a little from here to here, right? And now what we're going to do is take this, take the expression that we obtained for the perturbed Christoffel symbols and substitute here. I hope that it was clear what we did here, right? We identified the covariant derivative here because of the expression of this object as the partial derivative, and then the Christoffel symbol contractions with the object, and then we identify this as the covariant derivative and so on and so forth. But since there was no questions, I hope that you guys saw that what we did here. Anyways, no worries. If this wasn't clear, we can always come back to it. No worries. Okay, so substituting these terms, right? We get to this. Again, what we did here and here, we're going to substitute these terms with this expression here, okay? In each one of this. Okay, so the first term, right? This first term here becomes this, right? Which is basically what we used here is that the covariant derivative is compatible to the metric. So in principle, we would have to take the derivative of this object and do the product rule. But we know that the covariant derivative of the background metric, right? It's equal to 0, right? So because this covariant derivative is compatible with the background metric, okay? So in a way that what is left is this, okay? And so what we did here was to raise this index here, right? Using the inverse metric. So this is what we obtained finally, okay? With the first term. The second term is completely analogous, okay? So here, from here to here, we used the fact that in fact, what we did, we also used the fact that the covariant derivative is compatible to the metric. So what we did was the inverse operation, right? We plugged this inside each of the covariant derivatives, because we can always do this because the derivative of the covariant derivative of the metric is 0. So what we're gonna raise this index here. Here we're gonna contract with the derivative index and raise it right here. And here, let me just see what we did here with the metric. Yes, we raised it. Yes, we raised it. We exactly contracted this term with this term, right? This sigma and alpha is the same as contract this term to this term here, which is the same as contract with sigma here and raise it, so it became alpha. But since this is a dummy index, we can always change the label. So now we have this contraction here, right? This is what we did with this third term here, okay? In such a way that you can see that this term and this term here are equal, right? They're the same. So we subtract one from the other and get 0, and then we are left with this expression here, okay? Which here is the trace of the perturbation metric, of the perturbation tensor, okay? All right, putting these two together so that we can get this back, we get this, okay? If you remember what we did in Minkowski spacetime is very similar, right? We obtained second covariant derivatives with respect to the perturbations, right? And now finally, we identify the delta G mu nu with the perturbation that we used in Minkowski spacetime, right? Of course, it is not the same perturbation, right? But is the same in the sense that it is the perturbation tensor, okay? So delta G mu nu we identify as H mu nu, so that the equation becomes more friendly, and without this deltas all weird, and so we get this expression, which is very much simpler expression here for the Ricci tensor, okay? Which is very much like what we obtained, is very similar to what we obtained in the case for the Minkowski metric, right? And now if you take the trace of the Ricci tensor, remember we get the Ricci scalar. So taking the trace of the perturbed Ricci tensor, right? We get the perturbed Ricci scalar, okay? Which is basically take the trace, raise and identify the indices here, right? In such a way that we end up with this expression right here, okay? Any questions so far with all the development we did with the equation so far? No? Okay, so let's proceed and see what the Einstein equation, what the perturbed Einstein tensor is going to look like, all right? Okay, this is scary, but bear with me. Bear with me. We're going to get there, okay? So the full Einstein tensor, right, is this expression here, right? The full Ricci tensor, the full metric, and the full Ricci scalar, okay? What we're gonna do is open up each of these terms and distribute the operations and see what we get, okay? So from here to here, we open up this guy here, the full Ricci tensor, and we opened up and we saw that it is exactly as we defined in the first couple of slides, right? Here is the Ricci tensor for the background metric, right? And here the perturbed Ricci tensor, right? Here we open up the full metric as G mu nu ring and H mu nu, right? Here we open up the Ricci scalar, which is the trace of the Ricci tensor, right? So we open up here. Here is the full metric, inverse metric, the full inverse metric, and the full Ricci tensor, right? Just as we did here. What we are doing is just open this up as G mu nu inverse contracted with R mu nu, right? Not R mu nu, right? As G alpha beta inverse contracted with R alpha beta, right? Exactly what is happening here. So note that if we do this distribution here and contract this with this and this with this, we are okay. But we contract this one with this and we are okay. But this is the perturbation, and this contains terms of derivatives of H, which means that this contraction here of this term with this term here would lead to terms in second order in H, which we will disregard, okay? So what is left here is, well, the contraction of the background metric with the background Ricci tensor gives us the background Ricci scalar, right? Okay. The contraction of the background inverse metric with the perturbed Ricci tensor becomes this, okay, which is basically the same as this, right? And then we have this left, right, which is also in first order in H, okay? This is in zero order in H, this is in first order in H, and this is also in first order in H, right? Because this is the Ricci tensor for the background metric, okay? So here we have second derivatives of the background metric, but no perturbation tensors here inside this object here. So now we're going to do this distribution again with respect with these two tensors here, right? And the same principle applies, okay? So this, when we contract with these objects here, we contract with them all, we multiply this, all of these terms, we are not going to contract, right? But we're going to multiply, so we multiply this tensor by these scalars, right? This is a scalar, this is a scalar, and this is also a scalar, right? See that all indices are contracted, no free indices, so this These are all scalars, right? Scalar functions. So multiply with this and we are okay. Multiply this with this term and we are okay because he's in zero order in H. But multiplying this with this and this, we're going to have second order terms in H, right? So we're going to throw this out. And what we are left, if we separate correctly, we end up with this, right? So note that we separated the terms in zero order in H after all these distributions. This is in zero order in H and zero order in H. So they are not perturbative terms, okay? And we can identify this term here, this couple of terms here, as the original Einstein tensor, right? Pre-perturbation, right? If we turn off the perturbation, this is what we obtain, right? This is the Einstein tensor for the background metric, okay? And what we have left, this is in first order in H. This will be first order in H, first order in H, and first order in H, right? So what is left, it is exactly the perturbative terms and what we will identify as delta G mu nu, as the perturbed Einstein tensor, right? In such a way that we get the perturbed Einstein tensor here, okay? Any questions about this, this development? I know that I'm being very annoying with this, but I mean, if we lose anything, we are lost. We're gonna be lost. Okay, so I want to stop step by step and see if there is any question about the what we did here. So no questions. Okay, it also gives me a moment to drink some water. Okay, so let's go. Let's see. Uh, sorry. So for if our background metric is a vacuum solution, what I mean by that? Well, when you have the Einstein equations, you basically have G mu nu in one side, right? And 8 pi T mu nu on the other side. So we have the Einstein tensor on one side, and we have the energy momentum tensor on the other side, right? And we can solve Einstein equations in the presence of matter, but we can also solve Einstein's equations in the absence of matter, right? What we call the vacuum solutions of Einstein's equations, right? Which is basically to set G mu nu equal to zero, okay? So if we analyze what the full Einstein equation would be, considering the perturbation, but considering the scenario where the background metric is a solution, is a vacuum solution, in such a way that, remember that the full T mu nu could be decomposed into T mu nu ring, right? The source of the curvature of the source, the matter that is present for the Einstein equation, and the perturbation and the source of perturbation, the delta T mu nu. But since we are talking about the vacuum solution, right? So there is no matter present, right? Which means that T mu nu ring is going to be zero. T, which is the trace, basically the trace of this, will also be zero, right? And this means that G mu nu ring, right? G mu nu ring is equal to zero, right? Because the background metric is a solution of Einstein's equations in vacuum, right? Which is the same as to make G mu nu ring equal to zero, right? So this will be equal to zero, which means that this will be equal to zero, and this will be equal to zero also. Okay. Just a second. Just a second, guys. I have to mute here. So just for okay, I'm back. Sorry, people from the maintenance here have to trade something inside the room. So I'm sorry about that, but we are back. Um, so okay. So what were as I was saying, since the background metric is a vacuum solution of Einstein's equations, so the Einstein tensor will be equal to zero, which leads to the fact that the Ricci tensor will be zero, and which means that the Ricci scalar will be zero as well. Okay? So this is what we obtain, right? So note that here, this will simplify also our perturbed equations, because here we have terms in our ring, in our alpha beta ring, which are zero, and in which will simplify very much our equations. So when the background metric is a vacuum solution, we can simplify our Einstein equation by this, okay? So this is our perturbed Einstein equations when the background metric is a vacuum solution. If this is not the case, if the case is not that, then this would be the full expression, right? And G mu nu ring would also be a part of it. So we would have to solve the Einstein equation for the background metric first to know who these guys are, right? Who the Ricci and the Ricci scalar and tensors are, and so on. And then substitute them into this expression to compute the perturbed Einstein equations, right? But we are dealing here with a vacuum solution. We're going to deal with vacuum solutions. For example, the short shoot spacetime is a vacuum solution, right? The short shoot spacetime, for those who haven't seen general relativity before, it's basically the geometry outside of its spherically symmetric object. So we have a spherically symmetric object that is curving the spacetime around it, right? But we want to see how the spacetime looks outside of this spherical object. So we turn off, right, the matter the matter energy momentum tensor, right? Because here we are the model, right? The scenario is there is this spherical object and nothing else in the universe, right? So there is no matter outside of this spherical object. So the outside of the outside solution of Einstein equation will be a vacuum solution, right? If we were trying to see how the spacetime would be inside of a massive spherical object, for example, a star, if we're modeling a star and want to see what are the equations of motion for the fluids, or I mean the elements that compose the interior of the star, okay, we would do T mu nu different than zero, and we will model this energy momentum tensor in accordance with whatever we are using to, I mean, to model the interior of this star, for example, okay? But since we are looking at the exterior of the spherical object, so there is no matter there, so we set this equal to zero, and what is left here will be only, in a case of perturbations, the only thing that will be left is the perturbation, the source of the perturbation, right? The delta T mu nu here. Okay. All right. So Schwarzschild spacetime, we have this, right? We have R mu nu ring equal to R mu nu Schwarzschild is equal to zero. Okay. So this is an example of in which these equations will be valid when we do perturbations in Schwarzschild spacetime. This would be the equations that we'll be looking on. Okay. All right. So now we will take a little detour to talk about tensor spherical harmonics and the harmonic decomposition. Well, in this, when we are perturbing our spacetime with scalar fields, the decomposition are very simple to do. But when we are doing this perturbation with a spin 2 field, as we saw from the previous lecture, right? Our perturbation can be seen as a massless spin-2 field. When we do when our perturbations are of character of spin-2, this decomposition is a little bit more involved, okay? And to do this in the right way, so we can separate the radial and temporal parts of our perturbation and the angular parts of our perturbation, we're gonna have to use these tensor spherical harmonics and perform what we call the harmonic decomposition, okay? So, since we are going eventually to do perturbation in in Schwarzschild spacetime, and to fully take advantage of the spherical symmetry of this problem, we're going to introduce scalar vector and tensor spherical harmonics to separate the radial / temporal part of our perturbation and the angular dependencies, okay? So, what we are doing mathematically, okay, for those who are worried about how we are going to do this in terms of structure, what we are doing basically is we are modeling our manifold, our full manifold, as a cross product between this manifold M2, which is going to be taking care of the T and R coordinates, right? And S2, right? Which is the two sphere, right? And so we can model our space-time, we can decompose our space-time in such a way, okay? We depart from the fact that we can do this in such a way that the coordinates of our space-time will be also decomposed into Z capital A components and Y A components, okay? These Z capital A components are the, coordinates. These coordinates are the T and R coordinates, okay? And the YA coordinates will be theta and phi, okay? So A runs from 0 to 1, and A runs from 2 to 3, okay? In such a way that we maintain the fact that X mu runs from 0 to 3, which means runs from T, R, theta, and phi, okay? Basically. So this, which means that what we are doing point by point is to decompose our tangent space, our vector spaces, right? We are decomposing the tangent space at P into this tensor product, right? So at each point, what we had earlier was a vector space, right? A TPM, which now we are decomposing to a TPM2 tensor product TPS2, okay? At each point of the manifold, okay? So vectors will be described as this, okay? In our manifold, T mu. Remember that this is also a two vector, and this is also a two vector in such a way that this is a four vector, okay? A runs from 0 to 1, and A runs from 2 to 3, okay? And 0 to tensors, right, can be represented as this, okay? Remember, so this is a 4x4 matrix. This can be represented as a 4x4 matrix, right? Which means that this is a 2x2 matrix. This will be a 2x2 matrix. This also and this also will be a 2x2 matrix, okay? But this is completely, this 2x2 matrix only has only has functions in terms of T and R. Here we're gonna have functions of T and R and theta phi combined, also here. And here we are going to have only functions and components that are functions of theta and phi only. Okay? Is that clear for everybody? What we're gonna do here is gonna become, I think it's gonna become more clear as we advance. But if there's any questions about it so far. Okay, so this demands that we decompose our objects not only in scalar perturbations, right? because when you do perturbations, scalar perturbations, all you have to do is decompose these scalar functions, right, that are perturbed in your spacetime and that represent some field, some scalar field. You can decompose them into radial parts and this and angular parts using only the usual spherical harmonic, the scalar spherical harmonic that we all know and love from quantum mechanics and so on. But now that we are talking about perturbations of spin 2, our perturbations need other types of spherical harmonics, which are the scalar, the vector, the vector. I'm sorry, I got mixed up here. So the scalar spherical harmonics, the vector spherical harmonics, and the tensor spherical harmonics. Okay. So now let's enter the realm of the tensor harmonics. Let's enter the manifold S2 and see how these objects behave, because there are some properties that will be of very much of use to us so that we can do the decompositions and then the separations, okay? So if we define gamma AB as the metric on the two-sphere, such that gamma AB can be represented as this matrix, okay? We know that exists a covariant derivative defined on the two spheres such a way that the covariant derivative of the metric is equal to 0, right? So we're basically saying that there is a metric compatible covariant derivative in the two sphere, right? Also remember that the scalar spherical harmonics are basically the eigenvectors of the Laplacian operator, right? Which I will write as this L here, which we can decompose and represent as this operation here, right? Which is the second derivative, the second covariant derivative, right, of this scalar function, right? And this is equal to minus L, which is this number here, this what we I'm sorry. Well, this what we used to see in quantum mechanics as these quantum numbers here, right? And this identifies the spherical harmonics, the scalar spherical harmonics as the eigenvectors of the Laplacian operator. Okay. I'm not going to prove this to you guys. Okay. If you need to recall this, may be free to do so, but unfortunately we don't have time to do a review on that here. But okay, so now we know how scalars they behave very well because we are used to using them. But what about vectors? Okay. Now these functions, right? Since we are talking about a spherical symmetry, okay, we are going to decompose and subdivide our vectors and tensors, spherical harmonics, into what we call polar/even vectors and tensors and axial or odd, okay? We can identify them as polar or axial, or we can identify them as how they transform under parity. But we're going to talk about this in a moment. So now we're going to define the polar/even. So I'm using both of the labels because depending on which reference you go to, this would be called either polar or even. Okay, so I'm using both here so that we can that I can provide to you all a way to connect one reference to the other. Okay. All right. And now we have the axial/odd vectors. Okay. The polar, if I'm going to be calling them even and odd. Okay. But remember that they can also be axial and polar. Okay. But the even vectors are defined as this, okay? So we have a covariant derivative with respect to a given coordinate, right? And we have a covariant derivative with respect to the other component here, right? This should be theta and phi, right? I guess I made a mistake here also. I'm going to correct them before I send it to you guys. But yeah, this should be theta and phi here instead of A and B, right? It makes no sense, this but okay. So yeah, here we have it right for the odd vector. But yeah, so you take the covariant derivative with respect to phi of the scalar and with respect to theta, and you form this vector, right? And here, what we are doing is also taking the covariant derivative, but we're gonna have this I forgot the name of this the Levi-Civita, right? Is a two-dimensional two-dimensional version of the Levi-Civita tensor, right? So we apply contracting with the covariant derivative, we're going to obtain this expression here, which also involves first derivatives of the scalar functions, right? You see that the covariant derivative here became the partial derivative here because we are taking the covariant derivative of a scalar, right? Remember that the covariant derivative of a scalar must reduce to the partial derivative, right? The action of the covariant derivative must reduce to the partial derivative when acting on scalars, okay? It is exactly what we are doing here. So I know, guys, it's very overwhelming, all this. I suppose it is. It was for me when I was first learning them, but the focus here is only to present them, okay? Why and how they are constructed are not on the scope of this mini course, okay? But they are constructed in a way that we are able to decompose our metric perturbation in a convenient form for us to do the separation of the angular part and radial parts later, okay? So now we define the 0-2 tensors, right? They are ugly, okay, but don't hold it against them because they're going to be very useful to us. So no shaming, okay? So this is what we're going to get. This is the polar / even 0-2 tensor, right? Which is constructed thusly, right? These guys, we're going to define these scalar functions here, we're going to define who they are later, okay? And here we're going to have this other axial / odd tensor, 0-2 tensor, which is constructed in this form, okay? And this are defined as this, okay? This XL and this WLM, XLM, are combinations of derivatives and second derivatives of the scalar spherical harmonics, okay? So note that all of them use the scalar vector, the scalar spherical harmonics to build the vector. We did this here. We used the scalars to build the vectors by first derivatives and combinations of second derivatives of the scalar functions gives us the 0-2 tensors, okay? Where these elements are defined as such, okay? Some properties that will be important. Well, the 0-2 tensors are always symmetric, okay? And they are also traceless, right? So if you take the trace of each of this will be equal to 0. You can prove this by yourselves. You only have to do apply the metric, the inverse two-sphere metric here, and you're going to see that this exactly equals minus this, and so this equals to 0. And the same goes for this 0-2 tensor here, okay? It's a good exercise. I don't know if you guys are practicing this index gymnastics at home with the nasty calculations that we are doing here, but it's a good practice. Okay, if you're not doing now, you're gonna have to do it sometime. So we're going to focus now on the properties that will be the most um the most useful for us, which are the orthogonality properties. Okay, so give me 2 minutes, guys. Okay, let's define what it means to take a scalar product on the two-sphere, right? Scalar products always depend on the metric. So if a different manifold has a different metric, we have a different definition of what a scalar product is, right? In the two-sphere, right? This is a definition between of the scalar product between two scalar functions, okay? Basically. Is there any questions or just, oh, I think not, right? Sorry. So Victor, once again, if there is any questions on the chat, you can always interrupt me. Okay. So I'm considering that you already know this. So I'm gonna proceed. So this delta omega is exactly the two-sphere differential, right? The two-sphere volume, which is basically sine theta, d theta, d phi, right? And so, which means that to take the scalar product between two different scalar spherical harmonics is to take the complex conjugate of one of them multiplied by the first, take the integral in the two-sphere, and this will be equal to 1 if both L's are equal and both M's are equal. M and L is equal to L prime and M is equal to M prime. Okay. Otherwise, this will be 0. Okay. The scalar product for vectors, right? It's basically this operation here, right? The vectors, the scalar product of vectors contracted with the inverse metric, right? Which is basically to take the complex conjugate of one vector, and you see that the mistake is repeating here, which this should be, right? This should be theta and phi. So I'm gonna correct this all when I get home, but before I send the slides for you guys. In such a way that when you take the derivative over the two-sphere, this renders this expression here, which basically is L times L plus 1, and the Kronecker deltas here, right? Which will be 0 for anything for everything unless the L's and L primes are equal and M primes are equal. Okay. The same thing will happen for tensors, but when you do this operation, right, taking the complex conjugate and contracting with the inverse metric and taking the integral over the two-sphere, this will render us L times L plus 1 times L plus 2, and then the Kronecker deltas here, right? The L and L prime, M and M prime, which will be 0, which will always be 0 unless L and L prime and M prime are equal, okay? Okay, so note that if we have a full manifold tensor, a tensor T mu nu, okay, remember that we decomposed that tensor T mu nu into this object here, okay? But you must see that these objects will not all be tensors with respect to the metric in the two-sphere, right? Remember that this doesn't have any functions of theta phi. right? And here we don't have any functions in T and R, right? And here we have mixed functions. So, which means basically that with respect to transformations in the two-sphere, i.e. rotations, this object here, this 0-2 tensor, right, is not a tensor with respect to this metric, with respect to the S to the two-sphere, right? It transforms completely independently with respect to transformations in the two-sphere, i.e. rotations, right? In such a way that as far as the two-sphere is concerned, this object is a scalar, right? This object here transforms as a vector, right, in the two-sphere, because even though it has two indices as does this, only some objects composing this tensor, right? Remember that the multiplication of components of a tensor gives us a component of another tensor, right? So we could think of this as a YA times a R capital A, right? So the YA transforms, but the R capital A does not transform with respect to rotations. So this, as far as the two-sphere is concerned, it transforms as a vector, so it is a vector, okay? And this, since all the objects here have small caps indices, right? This is the trick, right? If you see capital indices, this means that this object is fully not spherical, right? And I don't know if that is the right term, but they're completely non-spherical, and these are completely spherical, right? And these are some kind mixed, right? So all the elements that compose this part of the T-mu tensor transform as a 0-2 tensor, right? Because both indices here transform under rotations because our indices concerned with theta and phi, right? So we may construct a basis with the tensor spherical harmonics. One may prove, this is not a proof that we will do here, and to find a proof of this, I don't really. I think that the book by Ferrari and Paulo, they give you the reference in which they do this proof, but they don't prove in the book by themselves, right? So the references, the references themselves that I presented to you don't do this proof, but you can always find them, find the references for the proof in the references. Okay, is a reference section. So, okay. So one can prove that the set of all the scalar spherical harmonics, they compose a complete basis for scalars in the two-sphere. The vector spherical harmonics here, the polar and even, the even and odd vectors form a complete basis for vectors in the two-sphere, and the odd the even and odd two tensors form a complete basis for symmetric and traceless a priori. A priori, we are dealing with symmetric and traceless two tensors in the two-sphere, right? So far we don't have a complete basis for general two tensors in the two-sphere, right? At first, because right, these guys here, they are traceless and they are symmetric. But we can always decompose a 0-2 tensor, a two tensor in general, by like this, okay? In a traceless part, right? A traceless part plus 1/4 of this composition here, which is the trace of the full tensor, right? Times the metric, right? So we can always decompose two tensors. Any two tensor can be decomposed in such a way. If they are traceless, well, this will be equal to 0, right? Which means that TAB is equal to the traceless part only, right? The same way that symmetric and antisymmetric parts work, right? We saw how to decompose tensors into symmetric and antisymmetric parts. Here we are decomposing the tensors into traceless and trace parts. This is the trace part and this is the traceless part, okay? So note that these tensors, right? This spherical tensors, 0, 2 tensors, they will take care of the traceless part. So they form a complete basis for this part, right? Because we're talking about symmetric tensors only, okay? So they form a complete basis for this element here. And since we have scalars, right? We have the spherical harmonic scalars, they will form a complete basis for this element here, which is the trace part, right? We have this in our manifold, and we have a complete basis for this part because we have that the scalar spherical harmonics form a complete basis for all scalars in S2. And this is a scalar in S2, right? So we see that with this will take care of the traceless part, this will take care of the trace part, in such a way that we have a complete basis for all scalars, vectors, and symmetric two tensors, right? Traceless or not, right? So this is a complete basis. All these sets together form a complete basis for any scalar vectors or symmetric two tensors in S2. Okay. So we said this set can be subdivided as seen previously. Well, this will be what we call the even tensor harmonics, right? And this would be the odd tensor harmonics, okay? In such a way that when we compose our metric perturbation, the functions that are multiplying the even tensor spherical harmonics will be even functions. And the functions that are multiplying the odd tensor spherical harmonics will be known as odd functions, okay? So this even odd labeling is the same as saying is a subdivision of this tensor spherical harmonics based on basis on how they transform under parity. If you do a parity transformation, which in the two sphere is basically doing this transformation here and this transformation here, right? From theta to theta minus pi and phi to phi plus pi, okay? So the even functions, the even tensor spherical harmonics transform like this, okay? Not only y, but also ya and za, they all transform as such, and the odd all transform as such, okay? So this difference in how they transform under parity ends up giving them the name of even and odd, okay? So this is why we call this and this even and odd respectively, okay? So let's get back to the harmonic decomposition. So we subdivided our manifold, right? In this form, okay? So we're gonna decompose our metric perturbation in this way, okay? The same way we did with the previous 0-2 tensor that we saw, right? Remember that with respect to the gamma AB, to the two sphere metric, these components will be scalars, these components will be vectors, and these components will be tensors. But with respect to T and R, right? With respect to the metric of this manifold here, is the inverse, right? I hope this makes sense. This is exactly the opposite. With respect to T and R, this transforms as a 0-2 tensor. This also transforms as a vector, right? Because they are mixed. And this transforms as a scalar completely, okay? Is there any questions about this? I mean, maybe it's a little bit confusing at first, but since we decomposed, right, our manifold, right? The objects that are present in the full manifold may have different characters depending on how they transform, right? So here we have this all angular transformations are in this part, and all the TNR transformations are in this part, right? Elements of this manifold that do not transform with respect to TNR, right? They don't transform in time or in the radial coordinate, right? But they transform with rotations. And here they don't transform with rotations, right? This is why we subdivide this this character of the terms in each one. It's going to be important for the way that we decompose each of these elements here, okay? So is there any question about this? No? Okay, so let's proceed and see how these guys are going to be decomposed in terms of our tensor spherical harmonics, okay? Okay, so here we have our, finally, we see how these guys look like. So H capital AB can be decomposed as this, okay? So we have a number of functions of TNR here in this H, L, M. So for every value of L and M, we have a function H capital AB here, right? And this is the basis, right? You see, remember that the scalar tensor harmonics form a complete basis for scalars, right, in the two-sphere. And here is exactly what we are doing. This is the basis, and here we have scalar functions with respect to the two-sphere, but not scalars with respect to the full manifold, right? So this as far as the two-sphere is concerned, these functions are scalars, right? So these are the components, and this is the basis, okay? But in the full scale, in the full manifold, this transforms as a tensor, right? The same decomposition we can make for the vectors, in terms of the tensor vector harmonics, the vector spherical harmonics, right? The even and odd, right? Here we have a even function and the odd functions, right? Which are vectors with respect to TNR, but that are scalars with respect to the two-sphere, okay? In such a way that this transforms as a vector with respect to the two-sphere and transforms as a vector also with respect to TNR, right? Because this transforms as a vector for TNR, this transforms as a scalar for TNR, right? They are invariant for TNR. Okay, and here is the decomposition of H as small caps AB, okay? Which is basically a decomposition in terms of the 0-2 tensors, right? And this also basis tensor, which is constructed with the metric and the scalar function, okay? So note that this, and this, right? This is the basis for the trace part. Remember that scalars, they are concerned with the trace part. These are the tensors that are basis of the traceless parts of this, and this is the basis of the trace part of this tensor, right? And they all transform as tensors with respect to the two-sphere, but are invariant under TNR. Okay. Is that okay, this decomposition here, right? We constructed the basis, right? We came here, we constructed this basis, and now we are using the basis to decompose our tensor, H mu nu, okay? So note that all of these functions are all functions of TNR, right? TNR, function of 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 TNR, right? And this would be a function of theta phi, theta phi, theta phi, theta phi, theta phi, theta phi, in such a way that these elements are functions of T, R, theta, and phi, okay? And this will be determined by the perturbed Einstein equations, okay? This will be the functions that will be the solutions to our perturbations, okay? Such a way that the subdivision of these functions can be done in the same way, right? In the same form of the as we did with the basis, right? Note that this object is multiplying, right? A odd, yes, no, wait, I'm always get confused with these names. An even tensor harmonic, right? The scalar is even, so this will be an even function, right? This would be an even function, and it is right in the name here, because there are two. So it's important to keep track of them. So that this is why we do the E and the O here. They stand for even and odd, okay? The LM are the numbers for the spherical harmonics, okay? So here we're gonna have an even function, right? An even vector, and this would be the odd, okay, which is here. So you note that this is multiplying a even function, right? So it is even. This is multiplying an even function, so is even. And this is multiplying an odd tensor, right? Which is why it is odd. Okay, so the subdivision is very intuitive. If you know which one of these are even tensor spherical harmonics and which are odd, you can subdivide the functions accordingly, right? Okay. Okay, so I guess we are over for today. I guess I didn't want to get too much into we did a little shorter lecture today because there are a lot of things, there are a lot of convoluted computations here, and tomorrow will be worse, okay? I'm sorry to tell you guys this, but let us retrace our steps to see what we've done today so far, okay? Let me just, oh my God. Okay, so we're seeing how the perturbed Einstein equations would be in the case of a general curved background. We saw how they would look like. We did all the same steps that we did from the previous lecture, right? We did all of the we found who are the perturbed versions of the Christoffel symbols, and then we found the perturbed versions of the Ricci tensor, right? Here we found we were developing the Ricci, I'm sorry, the perturbed Christoffel symbols. We saw that they transform as tensors. And then we saw and we derived the the perturbed Ricci tensor, right? Thusly, in such a way that it would look like this, right? We identified the delta G mu nu, right? Took the trace to find the Ricci scalar, perturbed Ricci scalar, constructed the Einstein equation, the perturbed Einstein equation, by doing all these steps, okay, which is the most safe way to do this, okay. Always keeping track of the terms in first order and getting rid of the terms in second order in H, okay. Then we identified this part as the original G mu nu, the original Einstein tensor for the background metric, right? And what is left all the terms in first order in H will be the perturbative terms. So they compose the perturbed Einstein tensor, right? So this is the Einstein tensor equation, the perturbed Einstein tensor for a general curved background metric. But when we are looking into vacuum solutions, we see that our equations simplify a lot, right? Because of the solutions of the background metric in vacuum are they go to zero, right? The Einstein tensor goes to zero, this goes to zero, this goes to zero, and so on and so forth. And so we get a much more simpler Einstein equation, perturbed Einstein equation, right? If you want to look to the perturbation far away from sources, just as we did in the previous lecture, we can always set this equal to zero, okay, and solve this equations for the homogeneous version of this, right? In the Schwarzschild spacetime, we have a vacuum solution as background metric. So, and then we the verb conjugation now slipped my mind. Okay, but we went to the realm of the two-sphere and to derive the tensor spherical harmonics here. Okay, so we took advantage of this and we did break our manifold into two manifolds, and then which means to break up our vector spaces, right? Our tangent vector spaces and so on, and thus we presented and constructed the vectors, the vector spherical harmonics, right? And then we constructed the tensor, the 0-2 tensor spherical harmonics, right? All to be used as basis, right? Basis for vectors, for scalars, vectors, and tensors in the two-sphere, okay? We saw some properties of them. We saw, which we're going to use a lot in the last two lectures, right? Which are the orthogonality properties, right? Which will help us separate the angular part from the radial and temporal parts, okay? We see that if we do this multiplications and the integrations by in the two-sphere, we get the simplifications, right? The orthogonality properties, okay? And then we saw that the tensors from the full manifold are not of the same character in two of the composite manifolds, right? For M2, they can be seen as one thing, but they can be seen as different things for the two-sphere, right? And we saw that the scalar vector and 0-2 symmetric and traceless spherical harmonics form a complete basis for any scalar vectors, vectors, and symmetric two tensors in the two-sphere. Okay, we saw this. We subdivided them according to the transformations under parity, which is why we call them even and odd. Okay, this is not going to be very useful for us. It's just a way for you to make reason of why they are labeled this way, right? In many references, they are labeled this way. In some other references, they are just called polar or axial, okay? But they are completely interchangeable. And then we saw how they transform, and then we applied this basis and decomposed our full metric perturbation in terms of this basis, okay? In such a way that we can subdivide these functions also into a odd part and an even part. So in the next lecture, we will see that we can always break this h mu nu into a h mu nu even and an h mu nu odd, right? And this separation will help us a lot because we're gonna do the perturbation of the Einstein tensor separately, Okay, we're gonna construct the perturbed Einstein the perturbed odd Einstein tensor, and then we're gonna and see how these equations look. And then we're going to construct the even perturbed Einstein tensor. All right. So imagine that here, sorry, just a second. So imagine that here, we're going to have 2 times this. We're going to have a even equation and an odd equation just by the separation of the perturbation into 2 parts, right? Into the even and odd parts. Okay. So it's gonna be broken up into a even and odd parts. This will also, and this will also. Okay, this is the background matrix, so we will not do the decomposition. Okay, so this is what we're gonna do. We're gonna construct the Einstein tensors, the even and odd Einstein tensors, right? Because they're gonna be respectively the even Einstein tensor will lead us to the Regge-Wheeler equation, right? And the odd Einstein tensor will lead us to the Zerilli equations, right? Which are the analogus, which are the analogs of the wave equation that we saw for the flat metric perturbation, right? So I guess this is it. So the goal to the end of and until the end of this mini course, the goal is so that we can get to the Regge-Wheeler equation and the Zerilli equation, which are the analogs for the wave equation that we saw for the flat metric. Okay, we will have 2 kind of wave equations here because we have 2 parts, right? We have an even and an odd parts that are completely separate, okay? So this is it. So I see you guys tomorrow when we will, I hope that we will get to the Regge-Wheeler equation, at least to the even Einstein equations I'm sure that we can get, so that we can construct this. And that's it. I thank you all for the attention. And if there is any questions on any computation that we did here, I think now it would be a good time for you to ask them. So you can come fresh tomorrow for the even more convoluted computations. So is there any questions?